And now up to the stage, Stephanie Dick from the University of Pennsylvania.
Thank you so much, Meredith and Kate. So at least as early as the 19th century, pioneers of mechanical calculation imagined that we might be able to one day build machines that would automate or take over human mental labor in the same way that factory automation and industrialization at the time was taking over certain kinds of human physical labor. And that vision is in some ways being borne out today as increasingly elements of cognitive labor, knowledge construction, problem solving, calculation, modeling, tasks that once belonged to the variously trained heads and hands of human beings are performed increasingly by automated systems. But as historians of computing have shown time and again, and as we've just heard from Karen, computers seldom simply replace people in the performance of a given task, but rather through automation, tasks are reimagined. They are transformed so as to accommodate or to capitalize on the affordances of the machines that we have built. And these transformations, especially where cognitive labor is concerned, often have really significant epistemological stakes. And that's what I would like to point to today. And because I'm a historian, I'll offer a historical example that comes from the early history of a field called automated reasoning that sought to introduce computers to mathematical theorem proving and mathematical problem solving. The example poses the question, what is it that we know exactly when cognitive labor gets automated in different ways? Where is that knowledge situated? Who knows it and how? So in the beginning, in the 1950s and the early 1960s, automated reasoning was imagined overwhelmingly in anthropomorphic terms. Practitioners imagined what kinds of contributions computers might be able to make to mathematical problem solving as measured against the different kinds of contributions that people make. So for some, they thought that one day computers would become just like human mathematicians. They could be colleagues or mentors or coworkers. Others were less optimistic, imagining the computer would be more like a graduate student and would be in need of significant guidance. Still yet others, in the tradition we heard from Simone about this morning, people used the language of servitude and slavery to talk about the kinds of contributions they thought computers would be able to make, specifically that they would do repeated menial tasks primarily. And through each of these anthropomorphic imaginaries, practitioners partitioned the work of mathematical problem solving and distributed it differently among humans and computers perceived as having different capacities or training. And in so doing, they also valued and devalued, humanized and dehumanized certain forms of cognitive labor. But this was only in the beginning. The anthropomorphic language of the field changed somewhat during the second half of the 20th century, as many practitioners wondered what forms of reasoning or problem solving computers might be capable of that were utterly unlike their human counterparts. Here, for example, is a quote from John Allen Robinson in 1965, who imagined remaking our very idea of reasoning and the logics that capture it with computers in mind rather than people. Traditionally, he writes, a single step in deduction has been required for pragmatic and psychological reasons to be simple enough to be apprehended as correct by a human being in a single intellectual act. When the agent carrying out the application of an inference principle is a modern machine, the traditional limitation on the complexity of inference principles is no longer very appropriate. More powerful principles become a possibility. So Robinson is most famous for what's called the resolution paper, principle, which he introduced in this same paper, which was intended to be one of these computer-oriented, more combinatorially powerful principles. So rules like the syllogism, Socrates is a man, all men are mortal, therefore Socrates is mortal, is meant to be obviously correct to us. Whether it is or it isn't is another question, but it is meant to be apprehended as correct in a single intellectual act, in his words. Resolution permits, on the other hand, more complicated inferences from the premises, all hounds howl at night. Anyone who has cats will not have any mice. Light sleepers do not have anything which howls at night. John has either a cat or a hound. We can infer with resolution that if John is a light sleeper, then John does not have any mice. This is, albeit a very baby prose example that's not actually that hard to work out, but it gives you the sense that resolution is a different kind of inference rule, not designed to be immediately apparent to us. And accordingly, resolution-based proofs and solutions were not and are not easy to unpack, to understand, to read and follow all the way through, if indeed that's even possible. But resolution was very powerful. Resolution took over automated reasoning. Resolution-based systems have been used to solve open problems in mathematics. They've been ported into industry to solve any number of problems. It is an exciting and a powerful vision, but it also has a number of critics. Those who believe that the human exemplar, human understanding and modes of reasoning ought not be dismissed so quickly because they fear that our understanding and our agency is dismissed along with it. They fear that such demonstrations can show us that something is the case, but not why. And I think the epistemological concerns raised by that kind of critique should stay with us as artificial intelligence systems move their way throughout many parts of our social world, not just mathematics. Thank you.
That was excellent.